So in our section, our next presentation from Yanlin Li. He is from Tianjin K Laboratory of New Energy, Automobile Power Transmission and Safety Technology, School of Mechanical Engineering, Hebei University of Technology. He is mainly engaged in the research and application of new energy vehicle powertrain system control strategies. His speak topic is energy consumption analysis of extended range electric vehicles with different driving cycle and different models.
My name is Yanlin Li. I'm from Hebei University of Technology. I'm very pleased to be here to join this forum. The title of my paper is Energy Consumption Analysis of Extended Range Electric Vehicles with Different Driving Cycles and Different Modes. My presentation will include these 4 parts. Firstly is introduction, some background information about this research. Nowadays, environment and energy problems are becoming more and more serious, and the government has introduced some policies to encourage the research of new energy vehicles. Therefore, electric vehicles are more promising. However, the current electric vehicle technology is not particularly mature and needs a technological breakthrough, so extended range electric vehicles are getting more and more attention. Extended range electric vehicle is mainly composed of engine, generator, motor, battery, and so on. In addition, the engine and the generator form the range extender. The motor is used to drive the vehicle, while the engine is only used to drive the generator and doesn't drive the vehicle directly. Compared with pure electric vehicles, a range extender is added, which can solve the driving range, battery cost, charging time, and other problems faced by pure electric vehicles. In extended range electric vehicle, when the battery doesn't provide enough energy to meet the driving needs, the range extender is studied, and the engine drives the generator to generate electricity. So there are 2 operating modes of extended range electric vehicles. After the range extender starts, it enters the hybrid mode, which can charge the battery or drive the motor to drive the vehicle. In this mode, the working state of engine is not affected by the running state of vehicle. And when the range extender is not studied, and only the battery is used as the energy source, it's the pure electric mode. Secondly, it's modeling and simulation. As shown in the left figure, the table is the vehicle parameters of the research objects. Based on the advisor simulation platform, the vehicle model was established according to the vehicle parameters as shown in the right figure. Next is the vehicle dynamics model. Vehicle dynamics performance refers to the motion characteristics of the vehicle along the driving direction. The driving force and driving resistance comply with the Newton's laws of motion. The driving force is equal to sum of driving resistance. The torque generated by the motor is transmitted to the driving wheel through the transmission system. At this time, the torque acting on the driving wheel produces a circular force on the ground. The ground's reaction force on the driving wheel is the driving force, which in the opposite direction to the circular force. So the driving force of the car can be expressed as this formula. When the car is driving on the level road, it must overcome rolling resistance and air resistance. When the car is driving on the ramp, it also needs to overcome the climbing resistance. As the car accelerates, it also has to overcome acceleration resistance. Then there's the engine model. The engine is the device that converts chemical energy into mechanical energy output. The working state of the engine has a great influence on the energy conversion of vehicle. The fuel consumption of engine can be expressed by this two formulas where the value of energy consumption rate is affected by the actual running state of the engine. As shown in the figure shows the effective fuel consumption rate of the engine, and then the motor model. In the process of driving vehicle, the motor has two operating modes, namely driving the vehicle as an electric motor or carrying out regenerative braking as a generator. Its operating power can be expressed by this formula. The working efficiency value of motor in the two modes is affected by the actual working state. As shown in the figure shows the motor efficiency. The analysis in this research is based on NEDC, WLTC, and CLTC. So the basic parameters of these three driving cycles are compared. As shown in this table, it can be seen that the proportion of idle speed in NEDC cycle is high, but the average driving speed in WLTC cycle is high, and frequent acceleration and deceleration are required in WLTC and CLTC. The following is energy consumption analysis. Firstly, is energy consumption in hybrid mode. The figures show the energy consumption proportion of each component and the energy loss per kilometer in this mode. Under three driving cycles, engine energy loss accounts for the largest proportion. The second is the energy consumed to overcome the driving resistance. Next, this research will analyze the energy consumption of engine and the energy consumed to overcome the driving resistance in detail. Engine energy loss include mechanical loss and heat loss. Among them, mechanical loss is caused by various friction inside the engine, so no additional analysis was done about it. Only a small part of the heat energy burned by engine is converted to useful work, so heat loss is the main factor that causes the engine energy loss. The simulation results are shown in this table. According to the simulation, the heat emission and heat loss power in WLTC are the largest, followed by NEDC, and the heat loss is the smallest in CLTC cycle. It can be calculated that the average engine energy loss per kilometer is the lowest in CLTC and the highest in NEDC, and NEDC slightly higher than WLTC cycle. And according to this expression, we know the air resistance is related to the vehicle speed, where the curve of air resistance charging with the speed is shown in the figure. So the speeds of three driving cycles were divided into low speed, medium speed, high speed, and ultra high speed, as shown in the table. Among them, the average speed of the WLTC is largest, and the proportion of high-speed interval in WLTC is the largest. In the ultra-high-speed interval, the proportion of WLTC is the largest. CLTC is the smallest. The distribution proportion of WLTC in ultra-high-speed interval is much larger than other two driving cycles. The distribution proportion in idle speed interval is much smaller than other two driving cycles. The distribution of CLTC is relatively large in idle speed and low speed interval, but small in high speed and ultra high speed interval. Therefore, the most energy loss to overcome air resistance is WLTC, followed by NEDC cycle, and the least is the CLTC cycle. When the weight of the car is constant, the rolling resistance is proportional to the rolling resistance coefficient, where the rolling resistance coefficient is related to speed. So according to the figure, it can be seen that the rolling resistance has little or no change when the speed is less than or equal to 125 km per hour. Therefore, according to the parameters of three driving cycles, the energy loss to overcome the rolling resistance is basically same in three driving cycles. Next is the energy consumption analysis of pure electric mode. The figures show the energy consumption proportion of each component and the energy loss per kilometer in this mode. Under 3 driving cycles, the energy consumed to overcome the driving resistance accounts for the largest proportion. The second is the battery energy loss. Next, this research will analyze the energy consumption of battery in detail. Then, the energy consumption of battery is mainly related to its internal resistance and the degree of charge and discharge. In a certain temperature range, if the temperature increases, the charge and discharge efficiency of battery will increase. The simulation results are shown in this table. It is calculated that the average battery energy loss per kilometer is the highest in WLTC cycle and the lowest in NEDC. According to the simulation, the pure electric driving range is shown in the figure. When the vehicle is driven by pure electricity, it has the longest driving range under the NEDC cycle, and the shortest driving distance is in WLTC. The last part is the conclusion. By comparing and analyzing the energy consumption loss of range-extended electric vehicles under different working modes, the energy consumption distribution under 3 driving cycles were explored. The results show, firstly, in the hybrid mode, the energy consumption of the extended range electric vehicles is the lowest in CLTC cycle and the highest in NEDC cycle. At this stage, the engine loses the most energy. Therefore, when the engine works with low efficiency, pure electric drive should be used instead, so as to reduce the energy consumption of engine in the inefficient era. Secondly, in pure electric mode, the driving range of the extended range electric vehicles is the longest in NEDC cycle and the shortest in WLTC cycle. At this stage, the energy used to overcome the loss of driving resistance is the highest. That's all my presentation. Thank you for your listening.
So, Professor Li, do you understand? Professor Li? Oh, sorry. Okay. So, I asked Professor Li Ji will introduce himself to us, so we can see. Share the computer.